Hello, hello, hello. Good afternoon, Internet. Welcome back. We're the same math time, same math channel, right? Gonna try on a new phrase. We're here. We're here back with right NL Math Man, right? Math Man. It's like Batman. That makes sense to me, to us. Um, right. So today here we're back on day 43, and this is an extremely important day. All right. This is probably one of the two most important days of the year. Seriously. I mean, May 29th, it's really important. You want to know why? Well, why? Why is because today is little Smokey's birthday. There's a little buddy. Yeah. You see him in the picture here? He's the darker one, the little doggy, looking off to the left there, the one on the left. It's his actual birthday. We know what his actual birthday is because even though he was a rescue dog, um, we do know uh, like who his parents were or who his mother was at least, and we know when he was born, right? And it just so happens that he is exactly 6 years old today, right? So he's 42, kind of, right? He's six in people years, 42 in dog years. He passed me a while back, so now he's older than me. Oh, cute happy birthday. Yes. Yeah, little buddy's birthday. Uh, I'm sure I'm sure he'll get some very special treats today. Well, though he gets special treats every day, so I don't know. I don't know that he'll notice any different any difference between today and any other day. But, that's this little buddy there over on the side. We got had to get a picture with Sissy in it too, of course, right? Because, she's a good girl. And she doesn't understand why people are, pay attention to brother on his birthday. Although, to be fair, right? Like, I mean, it's not going to be any different for either of them because people give them a lot of attention and a lot of loving either way. There we go. So another look at little buddy. Zoom in a little bit on him there. So, yeah, for today, then I'm going to have a little bit of a change of pace, right? Not just math. I'm going to be doing a little bit of biology today. Um, yeah, I got maybe a little bit less banter than normal before we get into it because not 100% sure how long this one is going to take per se, but I should be just excuse me, around about normal time. I'm gonna do scale factors and similar shapes for transformations, perimeter and area of 2D shapes. Those are some fundamental topics there. I'm gonna cover the Punnett squares, the biology stuff first, even though it's third on my list. It's just I put it down there because I didn't want the word genes over my face when I was doing this part, right? I mean, that's important. Yeah, so see, it's another Friday, another Good Friday. It's the end of the month again, right? Yes, we had quite a few courses completed this month. It's yeah, it's going really well. Big congratulations to all the students that are finishing courses over distance teaching. I understand that it is, quite a bit more difficult sometimes to get work done, especially when you're at home and you can't get out and have a place dedicated to work, and you've got to kind of um, take home space that used to be just like recreational space or family space or whatever, and now all of a sudden that's workspace as well. That does, that puts some extra mental strain on you, right? Because it, sort of changes how you feel about being in that space, in that part of your house or whatever. And especially when you're like myself with quite a small apartment, right? There's not a whole lot of extra room to have, oh, this is the work room, whereas this is the fun room. Whereas now it's like, oh, this is the same room, and it's just here's the work time and here's the fun time, right? But we're all making adjustments. We're making do, right? Um, Maybe in the future, imagine a world where people have more dedicated workspace in their house, right? Because they're I don't know, being able to work from home becomes more of a priority in the future, perhaps. I don't know. We'll find out. Either way, yeah, people have been doing really well this month. So big congratulations to all the students but not only the people that are finishing courses, I mean, people that are handing in work of any kind, finishing activities and assignments and notes and stuff. It's really great to see the buy-in and to see people, you know, taking the opportunity to continue learning and continue their education, right? Like I said before, we are really lucky to be in a position where the work can continue and we can all continue, getting courses done and completing things, right? It's a time when there's a lot of people in a lot of industries and a lot of jobs, are just really stalled, right? Whereas we're able to keep on moving forward, maybe a little slower than before, but work with what you got, right? And it's great to be getting anything done right about now, I would say. Right? So again, big congratulations to all the people that are finishing courses. If you want your actual progress report for the month, I guess you can email me and ask for it, and I'll send it to you. I haven't been sending them out by default for this month or last month, but I mean, generally, you guys know how many courses you've got completed and how many you've got left to go, right? So, but if you want one, just fire me off an email, and I'll hook you up with that. Anyway, for today, now I'm going to, without further ado, I am going to get into the work for the day. And yeah, would every man be a biology man? Well, I mean, yeah, I guess so, right? Like that's my title kind of makes sense because right, a math man. Well, if a biology man is a man that runs on biology, right? Like they're made up of biology, whereas a math man is a man that's made up of math. I mean, that makes sense to me, right? I'm on the internet. I'm broadcasting, ones and zeros and, various color data and stuff. So streaming that at roughly 1,500 kilobytes per second straight to twitch.tv, right? So I'm a math man or a data man, information man. There we go. Yeah, NL info man. Maybe that's what I should have been. Anyway, here we are now. So over on the almost got it right. I almost pointed the right direction that time. Uh, well, I mean, I didn't. Right? There's only two directions. You can't almost get that one right. Anyway, so Emily, I believe who's working on this one now, I did send you a link to a video where I talked about this topic previously. This topic actually was on the third day of my Twitch streaming, right? Which now is no longer on Twitch. That video is not there, which is really too bad because those first few videos, like the first 5 videos I had like 30 something, 40 something views each, right? That's a lot of views for a VOD on Twitch, especially for a channel my size. But yeah, those ones are all gone now, so there's not really a record of the fact that those videos had. Maybe it was just a novelty, I guess, just people in different schools of checking it out, be like, "Hey, look at this guy, look at his awkward banter and weird cadence." Boy. Anyway, yeah, but you are able to see that video. I am going to go down through pretty much the exact same pages here today, but I'm going to maybe start from the start and go over sort of what it is that we're talking about. So the Punnett square basically is a way that we represent inheritance in genetics, right? And the Punnett square is surprisingly like kind of similar to some math topics that you'll see later on. It's called matrix multiplication, where you get like one row of numbers and then one column of numbers, and you multiply the row by the column, and then that fills out an entire like grid, right? And it's a really useful type of mathematics for multiplying like large batches of numbers together at once. It's the kind of thing that say data analysts or statisticians would do a lot of in Excel, right? And other sort of computer programs. So it is kind of similar to mathematics, but we're using the sort of this basic math foundation to represent biology information. And the information we're talking about here is how, in this case, plants, but how any living being inherits traits, right? So basically, like it says over here, right? This this began, or this notion of genetics began with Gregor Mendel, who was an Austrian monk, who was breeding pea plants, and he noticed that this was one of the first things that he noticed. This diagram over here is a really good job of representing that, and that is, I believe, page 529, page 529 in your text. So this is going to be, yeah, I'll start writing down. This is biology 3101C, and this is page. What did I say the page was? Boy, 529. Right? So over there, you see the short pea plant and tall pea plant. So what he did first was he took a short one and a tall one and then crossed those together. And he noticed that sometimes, and this is not true of every time he did it, but he noticed that often when he took a short and a tall and crossed them, every single offspring will be tall. That's odd, isn't it? Right? Because just just common sense, I guess, common sense, you would think that if one parent plant is small, one parent plant is tall, then you're going to get a mixture, or maybe you're going to get them all to be in the middle somewhere. But that's not what he found. He didn't find a mixture. He didn't find them all in the middle. What he found was that they all came out roughly the height of the tall one, right? That's a bit odd. Right? Why would you get that? And he found this like this was true like pretty much all the time. Now it's not always true, as we're going to see there now in a bit. It is possible to cross a short and a tall and get a different result, right? But about half the time, I guess, I don't know exactly the ratio, but about half the time when he crossed a short and tall, he ended up with all of them tall. That's weird, right? But then if he took those tall ones, the F1 generation, right, which it says over here stands for, what is that? The filial generation, the first generation. When he crossed those, he ended up with a 3-to-1 ratio. He ended up most of the time where there would be 75% of them will be tall, 25% of them will be short. Now, what the heck was going on, right? So these trials that he did with pea plants, and pea plants just because they were cultivating those in the monastery, and because obviously plants are way easier and faster to cross than like livestock would be or something like that, right? But over and over and over again, he got these results. So what was going on with that? Well, as we find out, um, basically there's two different types of um, I guess there's genotypic ratios, but I'm getting a little bit ahead of myself. But basically, okay, so traits are inherited through alleles. Now we're going to be looking at alleles for traits that are dominant or recessive, right? We're not going to be looking at co-dominant traits here right now. So just like everything in the sciences, like every time you learn anything in a science course, basically, especially anything in a high school science course, there's always this caveat of, you know, this is kind of right, but this is a simplistic look at it to sort of introduce you. And if you went on and did more studying, you're going to find that there's actually a lot more complication to it. So, keep in mind that what we're doing here obviously doesn't represent the entirety of how inheritance works, but it's a very simple way that some genes do indeed work this way, and it's a useful way to start thinking about the rest of them if you were to carry on and do more biology, right? So So yeah, traits are inherited through alleles, and alleles are represented by letters, right? So dominant traits are represented by a capital letter. So if there's one dominant allele, the dominant trait will be expressed. Um, then I'll say uh, recessive traits, of course. Okay, so recessive traits are represented by a lowercase letter. Recessive traits are only expressed if both alleles are recessive. Um, yeah, so I think, Emily, I think you're in chat there. But if you have any questions or if you're unsure about anything as I'm going, just type a message in chat and I'll see it and I'll respond to it as I'm going here. Um, Basically, let's see. So I want to get a few terminologies, a few terms out of the way before I can get into really talking in detail about what each of these things represent, basically. But then we have the genotype. There's two other terms we need, basically. So genotype refers to right? So genotype refers to the letters that we use to represent a trait. For example, two capital T's, a T and a lowercase t, or two lowercase t's being the genotype for pea plant height, right? So if I was to go on here and we took a look at over these ones, right? So let me just zoom in and I can leave this up on the side while I'm talking about some other stuff. We can see over here that yeah, so this is a tall plant with two capital T's, which means it's let's see. Yeah. I'll write out the definitions. So two capital T's. This one's called homozygous dominant, right? Because there's two capital T's. This one's called heterozygous, meaning one of each, right? And then there's homozygous recessive. And that's when it's two recessive traits, right? So this is two dominant traits for tall, right? Which is what we see over here. You see this pea plant that I'm circling over on the right? This one here is homozygous dominant, so it's got two T's, two capital T's. This one here is homozygous recessive, right, which is short. And then this one here, this one that results, this one is heterozygous because there's one capital and one small. Because as you see here, right on the side, um, basically the child plant or the F1 generation inherits one trait from each of the parents. Now, which trait it inherits is random, but we don't. But here it doesn't really matter, does it? Because both these are tall traits, both these are short traits. So it has to get a tall from this parent and a short from this parent. So it's always going to come out to be a mix or a heterozygous, right? And then there's one more term that I need to get over. We need to get covered over here on the sides. This is phenotype. So whereas genotype refers to sort of the letters we use to represent a trait, or the alleles, I should say, right? So the genotype refers to the combination of the alleles. The phenotype refers to the expression of the gene, or in other words, how it looks, right? Generally, it's how it looks. I mean, it could be how it smells, how it sounds, how it, I don't know, whatever, right? But what I'm saying is the phenotype is actually what you see, right? So in the case of Mendel's like immortal example of the pea plants, TT and TT have the same phenotype. Right, I put them in quotation marks just so you see that it's not that I'm being sarcastic or anything. It's just that to show that it's what I'm referring to. Anyway, um, and so phenotype refers to the expression of the gene or how it actually looks on the plant, right? So the two capital T's or capital T, small t have the same phenotype, which is tall, and the two small t's has a phenotype which is short, right? So if we Yeah, I should go fill these ones in. So capital T for tall was the example of the dominant trait, and small t for short. Now you might be tempted to use T and S here, but that's another thing I didn't bother to mention that because it's almost a technicality, but it is worth knowing that we always use the letter that represents the dominant one, right? So if we're talking about, say, I don't know, brown eyes are dominant and green eyes are recessive, right? The B for brown is going to be a big B, and the letter for green is going to be a small b, not a small g, right? But that's just how we do it when it's dominant versus recessive. Now again, right later on, if you go on and see stuff like codominance, you'll start to see some other representations going on. But I'm going to focus on the type of representations that we're doing here in this chapter, right? So, but remember now, when we were looking at Mendel's first example over here, right, we saw that there were two things that were going on. And now, armed with our definitions, with these terms on here, we should be a bit better able to understand what's happening, right? Because remember what happened here was that at first he crossed these two. This is the parent generation. We represent that with P, right? And then F1 is the yeah. I'll jot those ones down real quick down here below too, just so you have these definitions, right? So P is parent generation. F1 is first offspring or filial generation. F2 second generation. You see where I'm going with this. F3 is going to be the third. And etc. and so on, right? So it's just another few terms that we're going to need to know here. So P, like we see over on the side, is the parent generation. So that's what we're talking about over here, right? This P is the parent generation, or the original generation. F1, then, oh, I lost my cursor. F1 is going to be the first offspring, or the first filial generation. So that's these ones. And then F2 is going to be the second. But important to know, right? F2 comes by crossing F1. We don't deal with the original parent generation anymore, right? If we cross these ones again, well, that would just make a separate F1, right? Because these always sort of extend downwards, right? So F1 is a cross of P, but F2 is a cross of F1. F3 would be a cross of F2, and so on and so on, right? And it is important to keep track of the F number on here because, as you'll see, right, the sort of statistical breakdown of what gene you're going to expect to see and what ratio you're going to expect to see the genes in is going to change from one generation to the next, and it changes in fairly predictable ways, as we'll see. Right. So over here now, this is a look at what was going on in the first generation. Well, we knew that when he crossed two capital T's and two small t's, he ended up with a capital T and a small t for all four of the plants. Or all the plants rather. Not four. I'm getting ahead of myself here. I'm getting ahead of myself. For all the plants. But then he found once he crossed two members of the F1 generation, right? So this was a capital T, small t for both plants. If he crossed those two, he ended up with three tall and one short, right? So the phenotype or the phenotypic ratio, as you'll see down here, right? It says it's a 3-to-1 ratio of tall plants to short. The term that we use for that, like I said, is phenotypic ratio. And your book will start using those terms only like a page or two after this. It starts asking you for that, right? But what's the genotypic ratio here? Well, the genotypic ratio is 1 homozygous dominant, 2 heterozygous, and 1 homozygous recessive, which is over here. Even though both of the parent plants, in this case, were heterozygous, right? So 2 heterozygous can come out with homozygous dominant, homozygous recessive, or heterozygous, right? So why is that? How can we represent this a bit more rigidly so we can sort of anticipate this? Well, this next page in your textbook, this one is worth understanding as well, but we can sort of return to this one after. but it's showing a bit about probability, right? And this, what we've got here is a fairly simple probability lesson, but it's one that, like, if I was teaching a probability unit, which is one of my gripes with the current math program, is that it doesn't spend enough time on probability. That's just because I love probability. But right, it's so much more fun to represent it and to test it and to do labs in it and stuff, right? Because you can, I don't know, you can break out dice and cards and all the fun stuff. Um, but if you're flipping two coins, right, we know that there's half a chance of heads, half a chance of tails, half a chance of heads, half a chance of tails, right? And then if we, so there's, then if we go start combining these, well, if we flip again afterwards, right, there's a quarter chance that we end up with two heads, like if we flip a coin twice, right? And say, look, how about I've got these? I had some. Now these are good coins. Look at that. I'm not going to have anybody guess where these ones are from. I don't think. Although you could, if you tell me, if you can tell me shortly, you can maybe get another mark or two off. Look at those. Look at those. Look how fancy those are. Now, if our friend Slayer Darth was in chat, he would definitely be able to tell us what coins these are. It's a hint because they are indeed British coins, but they're not legal tender anymore. These are shillings. These are coins that are no longer we're part of the old British money system before they switched over to pence and pounds, right? Before they switched over to, well, they had pence and pounds before, but it wasn't a decimal system. But anyway, say I flip two coins, right? What's the result there? Well, I got heads and I got tails, so I got one of the middle ones, right? But there's only four different or three different combinations, really, right? So I can get heads on this one and heads on, or sorry, tails on this one and tails on this one. I can do that. I can get heads on both, or I could get heads tails, or I could get tails heads. Those four combinations are all that there are, right? That's just it for flipping two coins. And since the order doesn't really matter, then the two ones, then either, heads, tails like that, or tails, heads like that, that's the same, right? So there's a 50% chance that it's one of each, 25% chance that it's two tails, 25% chance that it's two heads, right? And that's just the sample space, as we call it in probability, for flipping two coins. It's the exact same thing for genetic traits that are either dominant or recessive, right? So just the dominant versus recessive traits that we're looking at now is the same thing. It's sort of two 50% flips. But how do we represent that? How do we represent that in a way that sort of makes sense for what we're doing in this biology, right? And not just say like as a sample space diagram in a math course or something like that. So we see this thing called the Punnett square, right? So this is a good example of a Punnett square over here, and this is from your page, page am I on now? 532. So Emily, I will send you copies of those notes afterwards. I know you haven't been doing much math or any math, I guess, since social distancing began, so you might not have been in a position to see much of the notes that I send out. But after this is over, I'll send you a copy of those ones and also a link to the video and all that, right? But it is always best to be in chat just so you can, let me know if there's any other questions or anything that's not quite clear or something else you'd like me to do another example of. You can just drop a message in chat and I will see it and get to that. Okay. So Punnett squares are basically a way to represent a genetic cross, right? Um, so in the Punnett square, we write one parent's genotype above the square and the other parent's genotype on the left-hand side. So you can see that over here, right? If you look back over here, we've got a homozygous tall parent and a homozygous short parent, which is the very first of Mendel's crosses, right? So we put the genotype for the parent is right here. You see capital T, and the genotype for the other parent is on the side here, little t, right? So I'm going to draw that out here now. So let me grab. So let's do it in black. My order came in actually. Walmart came through for me. I've got some brand new. I got some brand new pens. I actually ran out. My gel red pen ran out this morning, right? So I've got, but I actually managed to get some more. So crisis averted. You know, I thought I was going to have to start, doing everything in black or blue, right? But I managed to get some more red and green. So that's actually, this is a heck of a lot bigger than it needs to be. Boy, oh boy. But anyway, we'll see. It'll be very clear. So that's good. Right. So this is basically the Punnett square here, right? So we're going to have so the genotype of one parent is up here, and it's two capital T's like that, right? And I'm going to do these ones in different colors so we can sort of track a bit more clearly what's going on here. So this is going to be a lowercase t and a lowercase t, and this is it's the same sort of deal here, right? So this is the genotype of one parent, these two lowercase t's, and this is the genotype of another parent, these two uppercase t's. Then what we're going to do is basically, here now we just kind of multiply. This is like grid, right? So we just sort of fill in. Right? And this is what, actually, no, we'll see. I'm getting ahead of myself. We'll see in a second here. So we fill in the values horizontally for the left parent and then vertically for the top parent. What do I mean? Well, I mean, here now, in this top row, like we look at the this top row going across here, on the left is a lowercase t. So I'm going to go and I'm going to fill a lowercase t, a lowercase red in my case, because I'm using a different color, into both of these top ones here. So lowercase t there, lowercase t there. Same deal down here, right? So I'm going to go across because it's on the left-hand side. So it's going to have a lowercase t here and a lowercase t here. Now, for the top parent, we fill those in vertically. So this t is going to get filled in down through here. Capital T there, capital T there. And that's going to be the same thing now down through here, right? I'm going to take this capital T and fill it in vertically. Capital T here and capital T here. So now, this is the parent. This is one of the parents, this is the other parent. But now this, what we have here, this is F1. So this is filial 1, or the first generation that we've sort of found, right? So then F1 generation, we can see that all four of them, so it's going to be 4 capital T, little t, right? So we can call this, so this is the genotype, right? So we've got 4 heterozygous, yes, 4 heterozygous, right? Or there's going to be 4 tall, right, for our phenotype. So even though the parents are both different, we see that they inherit one trait from each parent, right? From this one, and one from over here, and we end up with 4 of the same genotype, 4 of the same phenotype, right? So this is what we call the P, or the P generation, right? The beginning one. So now let's, down below here, how's about I do F1, the F1 cross, right? And let's see what we end up with there. I'm going to have to maybe draw it a touch smaller. You still seeing this? Oh, I'm down a little. I'm down a little bit. Let me see if I can. It's tough to get it to be exactly getting the whole page, but I'm close here. I'm close. Right? So we go across there like so, and this is the F1 generation. Right? So I'm going to use, let's see, I'll use green and red again. So remember now, we're crossing two of the results from here, right? So I'm going to put this parent's genes in green. You needn't fill in this part where you point and say genotype of parent. I'm just doing that to show you what I'm doing here, right? Then the other parent, because we're crossing two of these ones, right? So if we're crossing two of these results, well, it's going to be big T and little t for both. So I'm going to put a big T here and a little t. And this is, again, the genotype of one parent. And just like we did before, I'm going to go and I'm going to fill in across, and then I'm going to fill in down, right? Now, it is worth knowing that we always write these if there's dominant, the dominant one always goes first. So we would never call this like small t, big T. That's a really small technicality. I'd not, I wouldn't necessarily dock marks from you for doing it on a test or something like that, but it is worth knowing that we always do the big one first. So when I go across here, if I've got a big T, I'm going to fill it in the first spot, right? So this capital red T is going to be in both these across here like so. This lowercase red T, I'm going to put second because I know that a lowercase will go second if there's two, if there's a uppercase and a lowercase. Now what I'm going to do is I'm going to go down and I'm going to fill in the green ones, right? So here's now a big T filled in here from this one and a big T filled in here from this one. Now a little t filled in here from that and a little t filled in from that. Now what have we got? Well, now this is our F2 generation, right? So if I say my F2, which is to say the offspring of the F1 generation, the F2 generation is going to have, let's say, genotypes are going to be 1 homozygous dominant, right? 2 heterozygous, because we see there's 1 homozygous dominant here, 2 heterozygous here, and then 1 homozygous recessive, like that, right? But then what are our phenotypes? Well, the phenotypes are going to be 3 tall and 1 short, right? Because these ones, this is a tall plant, this is a tall plant because tall is dominant. This is a short plant because that one's recessive. So our genotypes end up being 1 tall, 1 homozygous, 2 heterozygous, and 1 homozygous recessive, right? Okay, and you will be asked to give ratios, right? So if I was to say, let me squeeze this in right here on below. Come on, life cam. Yeah, well, I don't know why it just randomly, sometimes in the middle of the stream, it gets really dark on the cam. Like the light level doesn't change in the room. So the genotypic ratio is just going to be 1 to 2 to 1 of TT to TT to TT, like so, right? This is the gene, and this is the order that we usually write it in. We usually write homozygous dominant first, then heterozygous, then homozygous recessive, but you can write it out sort of like this. And then the phenotypic ratio is it's just going to be it's going to be 3 tall to 1 short. right? And that's just you've seen that sort of thing in math, the ratios. I mean, don't sweat those too much, but all you're really doing is writing out your results just with colons between them, right? The important parts about this is really knowing how to set it up and knowing uh, sort of what the generations represent. That sort of F1 represents the cross of P, whereas F2, um, is the result of crossing F1. Now, where this activity or this page rather is the exact one that I did before. I mean, it was quite a while ago that I did it. There is a video out there of me answering most of these questions. I'll go down through and I'll do one of these ones here now to show sort of an interpretation of how we would do these ones. But hopefully the definitions and the sort of tutorial that I've done so far today will help you answer all of these questions. Um, let's see here. So solving a Punnett square. Let's do one of these practice problems here now, just to show how it works. So in pea plants, round peas are dominant over wrinkled peas. Use a Punnett square to predict the phenotypic and genotypic outcome of a cross between a plant homozygous for round peas and homozygous for wrinkled peas, right? So this is going to be biology 3101C, and this is page 533. 533. And I'm going to do question 1. Okay, let's pop over. Let's give myself a little bit more space, right? Because that's enough. That's enough space over on the side to see what the question is asking. Okay, so we're using a Punnett square to predict phenotypic and genotypic outcome of a cross between homozygous for round and homozygous for wrinkled. Now, I mean, wrinkled sounds like it begins with an R, right? But you see that both of them are R's, like I said, because we use the letter for the dominant trait to be the letter of the allele that we're using, right? So since round is dominant, round begins with R, we're going to have capital R, small r, instead of like a capital R and then a small w, which might seem to make more sense at a glance, right? So we're crossing homozygous round. Okay, so homozygous round is going to be that, right? So I'm just going to put an arrow here and say that's homozygous round, like so, right? And then we want a homozygous wrinkled. That's going to be, this is homozygous wrinkled, right? And now I'm going to go through and just fill them in. Actually, tell you what, how about I do these in black, just so we can keep maintaining sort of seeing the difference. Although, I mean, it's going to be fairly obvious, isn't it? Because filling these ones in vertically, well, there's going to be a capital R and a capital R coming down this way from that R. And same thing over here. There's going to be a capital R there and a capital R there. And just the same way as going across here, it's going to be a lowercase r and a lowercase r, then a lowercase r and a lowercase r, right? So what was it asking? Use Punnett squares to predict the phenotypic and genotypic outcome. Okay, great. So we're basically done with this question now, right? So the genotypic, we can say it was 4 out of 4 are or we can call it 100% are like that, which is heterozygous. I'm not super particular about how you represent your answer. You could say 4 out of 4. You could say 100%. You probably shouldn't just say 4, because just saying 4, well, you know, as someone who teaches math, 4 by itself doesn't quite give enough information, but 4 out of 4, that's perfect, right? Because that shows it's all of them. Or 100% shows it's all of them, right? Um, and then phenotypic. 4 out of 4 or 100% round. Right? Because remember, phenotype is the expression of the trait. Genotype is sort of the way that we denote the trait with our alleles. like so, right? Yeah, how about I do the next one pretty quick actually, because now that I'm getting into doing the examples here, these aren't too bad, right? Get to them kind of quickly so you can see a bit more about how these work. So in tomatoes, a red fruit, capital R, is dominant over yellow fruit, lowercase r. Homozygous red is crossed with the yellow. It's the appearance of F1. All right, so let's draw out what that cross would look like. So, homozygous red. So red is dominant. So a homozygous red is going to be, we're using R's again, but it just so happens that, because red begins with R. So this is going to be homozygous red up here, right? And it's crossed with a yellow fruit. So yellow, we know, has to be two lowercase r's because yellow is recessive, right? And since yellow is recessive, the only way we're going to be able to get yellow is by having two small ones, like so, right? So let's have them be in red because that's appropriate. I'll leave the other ones in black just because I didn't want to put those in green. Anyway, so now I'm going to go down and fill in the the R's, right? Capital R, capital R, capital R, capital R, right? Then I'm going to go and fill in these ones. So what is the appearance of the F1 generation? Okay, so appearance means we're looking for the phenotype, right? Because the phenotype is the expression. So for part A of F1 generation is 4 out of 4 red. Four to four red tomatoes, right? Because we see here what our results are. All four of them are capital R, small r. And since red is dominant, red is going to be expressed here. What are the genotypes of the F2 generation if two plants of the F1 generation are crossed? Okay, good, good. Yeah, I kind of want to get to that, so let's do B over here. I'll do it in green to keep it distinct from the other ones. So I'm going to draw out another Punnett square, and this is going to be generating the F2 generation. Right? Okay, since we have, we're going to have capital R, capital R. I'm going to keep doing them in the same color as before, just so you kind of see how these ones end up getting mixed from the original parent, right? So this was the P1 generation, right? So this was P, and this is P, and this is heterozygous, or the F1, and this one here is heterozygous, also F1. So we're going to have two F1s cross, and then we're going to figure out what we're going to get in the end, right? So I'm going to go down, and I'm going to fill in a capital R in both these from the top. Capital R, like so. Down here, I'm going to fill in a lowercase r from this one, lowercase, lowercase. Now I'm going to do the horizontal ones. This capital R is going to get filled in across this way. So a capital there and a capital there. And this lowercase r is going to get filled in this way. And what is it asking us for in this question? It is asking us for genotypes of the F2 generation. So now it's asking for genotypes, not phenotypes, right? So F2 genotypes are going to be 1 capital R, well, 1 homozygous, right? To 2 heterozygous, one homozygous dominant, and then to one heterozygous recessive, right? So if I wanted to write out the genotypic ratio, what we would call this is one, the way we would write it is 1 RR to 2 RR to 1 RR. I mean, it's smaller, smaller, bigger, bigger, just like that, right? So that's, and then it says, what are the phenotypes of the F2 generation? Okay, sure. So the F2 phenotypes, right? Well, we know this one here, this is going to be, it's going to be tall. Sorry, this is going to be, what were we looking at? We're looking at red and yellow. So this is going to be red, right? This is going to be red, and this is going to be yellow. So the phenotypes are going to be 3 red to 1 yellow, or you could say it as 75% red, 25% yellow. Just some way that I know that you understand sort of the ratio that you're going to get, right? Because ultimately what these Punnett squares are showing is probability. Because, this is not necessarily saying that if you were to breed exactly 4 plants, you would get exactly 1 yellow and exactly 3 red. Of course not. What this is telling us is our expected probability that 75% of the time when you breed these plants over here, 75% of the time you're going to get a red tomato, 25% of the time you're going to get a yellow tomato. Now, if you only bred 4 of them, it's possible that you get 3 to 1, but maybe not. You don't really know what exactly you're going to get, but you do know if you bred like, I don't know, 1,000 plants from these, you're going to get very close to 75%, 25%. Maybe it'd be 77, 77, 23, maybe it'd be 26, 74, but it's going to be close. And the more plants you breed, the closer you're going to get to this exact percentage here. That's just an example of, it's a bit of cross-curricular stuff there for you, that this is just, it's basically just probability, right? But we're using this sort of, beginning matrix multiplication, which is kind of what this is like, just a very small matrix multiplication. And we're using that to determine the probability that the plants that we breed are going to be, in this case, either red or yellow, or in this case, round or wrinkled. Okay? So that's, boy, yeah, I was going on that one for a while. Hey, that was a solid 45 minutes talking about that biology topic. But I think that was a reasonably comprehensive look at it. Emily, if you have any other questions about this, or if there's any other examples you'd like me to do, or any questions from the text you'd like me to cover, please let me know. Once we're done here, like I said, I will send you all these notes. So if you didn't copy them down or screenshot them or whatever while I was going, don't worry about that. You'll get a nice pristine looking sort of scanned copy of them. Wrong window there. Here we go. Back on over here. Okay, so that was Punnett squares, dominant and recessive genes. Helped a lot. Thanks. Yeah, you're welcome. You're very welcome. Let me know if you've got any other topics that you want me to go over. For the science courses, I won't always do them on stream because sometimes it's more appropriate for me to just type something up and send you a paragraph or whatever. But for something like Punnett squares, where I can do out an example, I will definitely do those ones on stream. Okay, so I did want to also do introduction to transformations. It's at scale factors and cylinder shapes. Then maybe I will get onto the perimeter and area of 2D shapes like I mentioned yesterday. But that one's a pretty quick sort of topic. But the transformations are relatively quick too. Esther, I believe you said earlier, I guess she's probably not in chat because I believe she said earlier that she couldn't make the stream today, which is totally fine. I mean, that's what my past broadcasts are there for, right? That's why I've got those down below here, and why I've got the YouTube archive that I've sent out to students. And Betty Ann, I did find what you were talking about. If you click on my profile, like on the name NL Mathman, then you see the link down below. But Twitch updated its UI only like a few weeks ago, and since then, the way the links and my FAQ and stuff, they don't display below by default. You got to click on the actual word NL Mathman, which is sort of over over yonder, right? Over like, I don't know, far down below on the left-hand side is what I'm trying to point to. You click on that one, and then you'll get through to see my that old FAQ that I had with, some silly questions in it, and then the link to my YouTube channel where all the old archived videos are. Anyway, yes, I am going to do a little bit on transformations here now. So let me pull it up here. I'm going to close down a few of the files that I had open for that Punnett squares activity or lesson. And here we go. Okay. So this one is Math 3102C. And Esther, you have seen this kind of stuff before. I just kind of wanted to refresh your memory on it and to show you, how similar this topic is to some of the ones you've seen before. I imagine this topic is not going to be super difficult for you because it is, like I said, it is pretty similar to the stuff that you've already seen, just with a little bit built on. And the part that builds on actually is not too bad, right? Like sliding shapes one place to another. That's fairly easy, right? You just move it. You just hold it and just move it. I mean, you can literally do that if you use like tracing paper and you draw it out. You can literally just like physically move the shape across your paper, right, to see what it's going to look like in the end. It's actually a pretty good. It's a math hack, right? Math teachers hate them. Learn translations and transformations and rotations in this easy step. Use tracing paper, right? That's my clickbait. Anyway, um, so what it shows over here on the side, this is similar triangles like you've seen before. And how do we determine if triangles are similar or if any shapes are similar? Well, we find a ratio between the sides, right? Similar shapes also have equal angles, right? But we're not going to necessarily deal with that right this second. But the reason I bring up the similar shapes have constant ratio between the lengths of their sides, because this ratio, so this is the important term for right now. This ratio is known as the scale factor, right? So the scale factor, if you've ever made models or anything like that, or read maps or loads of stuff like that, anything small that stands in for something bigger in the real world, because that's usually how it goes, that has a scale factor, and it'll be listed on there, right? Like I remember I used to make model vehicles when I was like, I don't know, 9 or 10 years old, right? And some of them would be like, well, I don't know, 24-1 models or something like that. Like, 24 inches on the real thing was 1 inch on the model or something like that, right? I can't remember now. Sometimes you'll see like, I don't know, 100-1 models of like really big things, like the space shuttle or something like that, right? But what that ratio tells you is basically how much bigger the real object is, how many times bigger the real object is than the model or the small shape that you're working on. So the scale factor here, as we see for these two, that you didn't get a constant ratio, so we didn't get a constant scale factor. Here, for example, 2 tells us determine the scale factor used in the figures below and determine the width of the larger rectangle. So how are we going to determine the scale factor in a case like this? Well, the reason I bring up the similar shapes, which was a topic in a previous course, is because we find the scale factor by the same way we tried to determine if shapes were similar, right? So what we're going to do is, in this case, we've got a shape that's, all right, sorry, I thought it was 3. No, yeah, there we go. I wondered why that was off, but it's just because I had my page misplaced. Anyway, so for this example, right, it's going to be 2.3, excuse me, going to draw this out here now. So I can go through and finish this. Don't mind, don't mind me being so off. It's 13.8, and this is x, right? So since we're told these shapes are similar, we can divide corresponding sides to find the scale factor, right? So these two sides are corresponding. Let me put the cm back here, like so, right? So if we did 13.8 cm divided by 2.3 cm, that, as we see on the side, is going to give us 6. There we go. So since the scale factor is 6, we know that each dimension on the bigger shape is 6 times the dimension of the smaller shape, right? So now, say, since we know that, we can go and do, basically we know that x is going to equal 6 times 3.9. So we know that x then is going to equal 23.4 cm, right? So we can figure that one out afterwards. That's just one sort of small example, and your notes obviously have worked through that one for you already. What I'm going to do now today is I've picked a few questions from the text, some of which you have to do, I think, and some of which you don't. And I'm going to just, actually, it's only 2 examples that I'm going to do, because Esther, I know you haven't asked specifically about this topic yet. I just wanted to sort of preempt it and give you a few examples before you got going, so that you see how similar it is to some of the stuff that you've been doing previously, right? So I want to go to page 279 and then number 7. So 279. Let's go up over here, give you that nice picture of bees on the side there. Give me 5 bees for a quarter, you'd say. I mean, I had an onion on my belt, as was the style at the time. Now my students are like, what is this nonsense? Why is he just saying these random words? Cultured my cultured viewers who have seen, classic seasons of The Simpsons, they will understand. They will or people who, you know, shit post on r/Simpsons or whatever, right? These people will understand. Should switch back over here. So the Cape Spear Lighthouse is at the easternmost point of North America. It's true. It's true facts, right? Jody wants to build a scale replica of the lighthouse. The height of the actual lighthouse is 13.7 meters, and Jody wants her model to be 10 centimeters tall. What scale factor should she use? Now, I know that we've jumped right from a very easy beginning example straight to one that takes actually, a bit more work. But this is sort of what the questions are going to get like eventually, so I wanted to sort of jump ahead and show you the way these ones are going to work. So this is going to be page 279. And this is going to be question 7. Right. So we know that the actual lighthouse is going to be 13.7 meters, right? And then her model is going to be 10 centimeters. So how do I find how many times bigger this one is than that? Well, do I just go ahead and divide? Because over here what I did is I just took the big one divided by the small one, right? Do I take the big one and divide by the small one here? I mean, yes, but actually no, right? Before dividing, Come on, life cam. I see. I don't know why. I don't know why that keeps happening. But before dividing, convert both values to the same units, right? That's essential. So I know that um, 13.7 meters, I'm going to multiply that by 100 centimeters per 1 meter to go back to showing the unit canceling method that I was talking about just yesterday, right? We know that our conversion factor is 100 centimeters per 1 meter. So I have to arrange it so that meters are on bottom in here. On the bottom has to be the M. So then it's going to cancel. I mean, you probably knew that we just times it by 100, right? Like that's not that hard. But just, modeling good behavior to show how in the world, how exactly we're going to do it. So we know that the actual lighthouse is actually 1370 cm, right? So now we know to find our scale factor, I'm going to do actual divided by the model. Now you don't have to. You don't necessarily have to, right? Because we could do the scale factor the other way around too and get a different value. Totally fine. As long as you're clear what you're doing. As long as you state that you're doing, say, model divided by actual. But I'm going to do the actual one divided by the model, which is going to be 1370 divided by 10, which is going to be 137. Right? So from this, I know now that the so that tells us then that Jody should use a scale factor of 137. I'm just going to make sure that it's clear that that goes with this question, right? So that when you see it in the in the notes that I send, you won't be like, what in the world does this correspond to? Anyway, so what we had to do was before dividing, we had to convert both values to the same unit. That's super important, right? And to keep going along with my unit canceling, a scale factor has no unit, right? So we know that this has to be the same unit as this because we need to cancel the units out of here to get a value with no units for the end, right? I understand that might be, maybe it's a little bit confusing, but I do think about getting into the habit of thinking of your math as still having the units there actually helps out a lot in the end because it kind of prevents you from being able to make mistakes. Because if I ended up here with a value where my units were going to be meters divided by centimeters, that's not it's not quite right, is it? But anyway, so that's cm divided by cm, right? And it was important to have the units the same. But 137 is the scale factor. So I want to do one more here now for you, Esther, for this stuff, and then yeah, then I think you should be pretty well equipped to handle most of the ones in this unit, and then you can just let me know if there's any ones that you're finding difficult. I'm not going to talk about those pupils there, although I could. That's a topic that I haven't gotten off onto on the stream yet. I haven't talked about keratoconus like at all, but yeah, it does. I do. My eyes have all the time have different size pupils, just constantly, and it's because anyway. Um, but this is going to be page. Let's see, page 280, and this is going to be question 2. Right? And so question 2 on page 280 tells us two ladders are leaning the same angle against the wall. Two ladder are the two triangles the ladders make with the wall and floor similar? Explain how you know. Okay, so let's yeah, when in doubt, draw it out, right? Let's draw a diagram. That's the best way to get started with any question like this. Start off by drawing a diagram. So here's the wall, and here's the floor, right? A nicely bricked wall. It's a very, those are good bricks, aren't they, over there on the side? There's very Mario Brothers. It looks like, it looks like you should be able to slap that wall with a tail and like part of it'll break, right? or maybe some coins will pop out, or like a green mushroom if you're really lucky. I mean, you know what I'm talking about, right? That's the real stuff. Anyway, I'm really going ham on these bricks. I'm just gonna. There we go. Look at that. That's not bad, right? That's kind of Mario Brothers. Um, so now the ladders. I don't think there weren't any ladders in original Mario Brothers, were there? But there were vines, right? There were vines, the sort of green vines that you would climb, right? And those came back in three as well. I think two did have ladders, but two is a weird one. Two, I mean, any nerd will tell you that Mario 2 is not really Mario 2, right? It was Doki Doki Panic. Anyway, we're getting real deep with the cuts here, let me tell you. Yes. Let's talk about 8-bit video games for a bit. Hell yeah. So that's not that I'm a huge retro guy, but I do think that like, the forced creativity that the technological restrictions that were in games at that time had just really forced designers to do some absolutely brilliant stuff. Not that old games are necessarily better. There were plenty of crap, plenty of terrible games on the NES and other systems, but the good ones were like, boy, oh boy, the good ones were really works of genius. Um, so we know that this is 2.9 meters here, and this is 3 meters for this one, and we're told that this is 8 meters. And then, are the two triangles ladders make with the wall and floor similar? Explain how you know. Hmm. Hmm. Now, how are we going to know? I don't think we have enough. We don't really have enough information for this one, do we? Um, the 3 meter ladder reaches 2.9 meters up the wall. How much further up the wall does the 8 meter ladder reach? Well, oh, they're leaning at the same angle against the wall. Doy. Okay, there we go. Right? Like sometimes the teacher doesn't see it right away either. Hmm. Right? But there's something that the question told us. The question told us something that isn't actually represented in our diagram over here, right? Because the question also told us that they're leaning at the same angle against the wall, which tells us that this angle here, which I will color in a red arc, and this angle here in this red arc are the same, right? And we know that this angle here is 90 degrees. This angle is the same as that one. And if those two angles are the same, well, this angle and this angle also had to be the same because, of course, three angles in a triangle add to 180. So we can't have two angles the same. We have to have either one angle the same or three, right? So I could easily say that since the angles in the triangles are the same, the triangles must be similar. Or the triangles are similar, I could have said, to save myself a word. When in doubt, cut it out, right? That's like editing 101, baby. Just find ways to say things shorter, right? I mean, that's it's comedy editing too, and academic, all of it, right? Right? When you're doing comedy, right? Make it shorter, make it funnier. That's what you do. Um, 3 meter ladder reaches 2.9 meters up the wall. How much further up the wall does the 8 meter ladder reach? Okay, so to figure out B, we've got to get the um, sort of the conversion factor, right, between the two of them, or the scale factor rather. So to find the scale factor, right, we know that, say, the big over the small is going to be 8 over 3. So we know that our scale factor is indeed 8 over 3, right? Another way that we have seen these in the past, right, is to represent the scale factor as one side of a cross multiplication, right? So then the full height, which is, say, on up to here, and then on down to here, I'm going to call this height x, right? Because this is going to be the height of the bigger one, right? But we know that 8 over 3, right? That is going to be the same as, and that this 8 over 3 is going to be the same as x over 2.9, right? And this is a cross multiplication now. So this is just showing you sort of another way that we can apply our scale factors. But we know that this is 8, this is 3, right? And these are similar triangles. So we know that this is the big triangle over the small triangle. This one's the big triangle over the smaller triangle. And we know that this is true. So now we can go ahead and do our cross multiply. Right? And we're going to get 2.9 times 8 equals 3 times x. Right? Now I am running out of some space down here a bit, but I think you'll see here now in a second. 2.9 times 8, right, is going to be, so this is going to be 23.2 equals 3x. I'm going to do this out fairly painstakingly, like with a lot of different steps here. So then we're going to have 23.2 divided by 3 equals x. So what we're going to have then, 7.73 equals x. And there we go. That is how we're going to find out those ones. So Esther, hopefully that's a reasonably intelligible look at how we're going to be applying sort of some of the stuff that we studied before in a little bit of a different way in this unit, right? So now go back over to my intro screen. I wanted to talk about perimeter and area of 2D shapes. This one is fairly straightforward, but rather than putting it off for another day, I am going to go ahead and do a little bit of these ones. Right now, this is a fairly straightforward top. Oh my Lord in heaven! Boy, I don't know why I hiccup so much these days. Anyway, yeah, so I'm going to do a few on these. Not going to be long. I've got about 12 minutes or so before I would normally sign off. That's probably enough to tear down through a few of these examples, right? These are not super difficult questions. This is going to be Math 2017, Unit 2. I think it's Carly. You're about to start this one, I believe, because I think you should be just finishing up the end of Unit 1, I believe. You know, everything else you did in Unit 1 was really good, but you did leave that one page of the study guide out, so I am still waiting on that one before you can go ahead and write your test on Unit 1. But you seem to be getting all those topics, down pretty well, so I don't see there being a ton of review necessary for you to understand those topics. This is going to be page 170. And now, basically, one of the main things that we're doing here is just sort of telling the difference between perimeter and area. So perimeter is the distance around a shape. Around the outside. And then circumference is just the perimeter of a circle. Right? So to do 1A, all that is going to be the distance around the outside of the shape, which is just going to be 12 plus 12 plus 3 plus 3, which is going to be 30. Right? It's not super hard. You can literally just go and add all the sides up. Realize that that's a rectangle, right, in 1, although, even though we're not really told, honestly, and this is, I usually sing the praises of prism math, prism, prism math, right? I know before it sounded like I said prison. That was a good, it's true, it does seem like a mathematical prison. Anyway, we should be told, ideally, that these shapes have right angles here, and that way, because it looks kind of like they do, but generally it's a bad idea to make assumptions based on the shape of a diagram in a math course. But here you're going to have to for some of these ones, right? But then for B, the perimeter of this one. This is a square, so that's just going to be 4 times 5.2, right? Because there's 4 sides around a square, obviously, and they're all going to be 5.2, so that's going to be 20.8 centimeters. For C over here, now for this one, you have to have your formula to find the circumference of a circle. This is one that you have seen before, and it will be on your formula sheets, but it is important to know when to use it. The circumference of a circle is circumference is equal to pi times diameter. D is equal to diameter, right? R is equal to the radius. Diameter is equal to 2 times the radius. Oh, and then pi is approximately 3.14 we're going to use in this course. You'll hear me make fun of that sometimes. Like I say, I'm not about this 3.14 life, and I ain't. I ain't about it. You know, I like the 3.141592657985. Whatever. Like, put on the Hard and Firm song if you want. That is a dank song. But here now, we know that circumference is equal to pi times diameter, but we're not given the diameter over here, right? We can say, or circumference is equal to 2 times pi times the radius, right? So here what we have is C is equal to 2 times pi times, what is that, 28? Yes. So then we're just going to put that into our calculator. We're going to do 2 times 3.14 times 28, and we're going to be left with 175.84. That's in meters. I don't think you had to be concerned about the fact in this other one. I did just notice this, actually. I've never seen this before, that this one actually has the measurement in meters here, but it says cm down here. So I guess you could say it was 20.8 meters, or it was meters on the shape, or you know, that was probably a typo on the bookmaker's part, and not like a little cheeky way to try to get you to convert. But who knows? Maybe it was. Maybe, what do I know, right? Then for 2A, well, for 2A, we see that it's just a hexagon where each side is 2 meters. Now, again, it should realistically have a little notch there if we were supposed to know that each side was 2, but it's just going to be 6 times 2 equals 12 millimeters here for this one. 2B, like I said, I am going to go through these ones relatively quick here. 2B is another circle, so we know that circumference is equal to pi times diameter, which in this case circumference is going to be pi times 90. What is that? Boy, I'm having a hard time even seeing what that is. 96? Is that a 96 or a 98? My lord. 98. $307.72. Right? And then C. C is the one that I wanted, one of the ones that I wanted to do here just to show you, because if it's an irregular shape, like where all the sides are different, well, all we still got to do is just add those guys up. So it's going to be 3 plus 3.5 plus 7 plus 2.75. It's going to be 13.5 plus 2.75 is going to be 16.25. 16.25 centimeters. That's all. That's all you got to do. Right? So these are not super difficult questions. But again, right, I did want to go down through some of these ones just to show you. So then area is the next topic. Area is the amount of space Area is the amount of space a shape takes up in 2 dimensions. Now you're going to have different formulas to find the areas of different shapes, right? So, for example, number 3 here, in 3A, we know that the area of a rectangle is just length times width. So here now it's just going to be 7 times 2, which is going to be 14 km squared. Now you'll notice that in Prism Math, down here, they already have the units in for you, like down right there, right? But it is worth knowing that if it's kilometers this way and kilometers this way, it's kilometers squared, because what you're doing is you're multiplying kilometers together, right? So for B, even though it's on a slant, it's still a rectangle. So we're still going to use the same formula, length times width. And it's just going to be 7.2 times 3.5, which I'm not going to do in my head. 7.2 times 3.5, 25.2 meters squared. And then C here, C is one of the ones that I wanted to get on to talking about. C is a circle, obviously, right? And what's the area of a circle? Well, the area of a circle is going to be pi times radius. Actually, use the capital R above, so I'll keep doing that. Pi times radius squared. Now remember, squared means you're multiplying it by itself. You're not multiplying it by 2. It's a common mistake. People often lose marks on that kind of thing. And it's a shame to lose marks for that, right? Because you knew the hard part. You knew what formula to use. You just kind of didn't know how to put the number into the calculator. So I'm going to go 4 squared, which is just 4 times 4, 16, times that by 3.14. And I'm going to get 50.24 centimeters squared. I'm going to skip question 4 because I think question 5 is more relevant to get to, and yeah, I don't think I need to really beat all these guys to death that much, right? Question 5 then. So 5A, this one's a triangle. The area of a triangle is going to be half of the base times the height, right? Now, again, you will be given all these formulas when you're doing like a test or anything like that on a unit like this. But one way to remember that it's going to be half of the base times the height is because you can think of a triangle is always half of a rectangle, right? Like if we look over here at any of these rectangles or like this square, if we drew a line from this corner to this corner, we would slice it directly in half. We would have 2 triangles. Same with a rectangle, right? If we go from the corner to the corner and slice it, we're going to have a rectangle here, a triangle here and a triangle here. So the formula for the area of a rectangle is just the 2 dimensions multiplied together. For a triangle, it's the 2 dimensions, but then you take half of it, right? Because it's half of what it would be if it was a rectangle. So it's going to be half. The base is across the bottom. In this case, it's 4.2. And the height is also 4.2. So we're going to have 2.1 times 4.2. It's going to be 8.82. 0.82 centimeters squared, like so. For B then, right, so we've got the area of a circle again, which is going to be pi times radius squared. Now remember that diameter is equal to 2 radius. So here our diameter is 6 equals 2r, which tells us that 3 equals r. So that's a little bit of an aside. Well, not really an aside. We do have to do that for this question, but it's not figuring out the same thing. It's figuring out what we're going to put in there. So we're going to have pi times 3 squared, which is going to be pi times 9, which is going to be exactly 27. Oh my God, it's not. Don't mind that exact pi is exactly 3 thing. I keep making that reference. One day someone's going to laugh, but it's probably going to be me. Now, one reason that I wanted to tear down through these and do all these other ones is because I did want to get to 5C. 5C down here has a bit more going on that I want to mention. Right? We see down here, it's 30 millimeters this way and 70 millimeters this way. But what in the world do we do? Right? Like we don't know from here all the way over to the corner. Shouldn't we have to figure out this whole thing? But the thing is, whenever we find a triangle like that, the only thing that we're doing is the base and height need to be perpendicular, right? Which means they need to be at 90-degree angles to each other, which is what this is shown here. But as long as the two of them are at 90-degree angles to each other, they don't necessarily need to be measurements of the outside of the shape per se. right? Because the height, which goes from down here to up here on this shape, it's not actually one of the sides of the triangle, right? Because this side is going to be considerably more than 70. This side's going to be even more than that. So neither this 70 is not one of the sides of the triangle, but it is still the height because it's the distance from the base that we have picked to the highest point that the triangle reaches. Sort of the same up here, right? We didn't do this example, but the 7 up here is the height from the base to the highest point. So the same sort of deal we go down here. We go from the base to the highest point. What's that? 1,050, I think. Yeah. Yes. 1,050. There we go. So I think that should be a decent look at basically what you're going to be doing to get started in that unit. And Carly, yeah, I don't believe Carly, I don't believe you tend to watch the streams live, but I will send you this one, of course, and then well, I mean that's probably if you're hearing me saying this, you found out about it through me linking it to you. So I guess I don't really need to say it, do I? Yeah, imagine that. That kind of makes sense. Hey, so to pop back over to my intro screen to take another look at the little birthday boy, little fuzzy brown birthday boy there in the middle. What a sweet little baby. Um, oh, there he is too. Oh, how nice, right? Um, yeah, that's another week down, right? Another month even. Whoa, whoa, another month down. This is the last day of classes for May. So there we go. Another week of distance teaching in the books. That's week 9. Week 9 of my online classes. Week 9 of our distance program at the school where I teach. Super glad that you could be joining me. I really hope that this is helping you and allowing you to feel a bit more like we're back in class and more like you have all the same opportunities to chat with the teacher and to engage and to get your questions answered like we would have if we were on site, right? So, yeah, I hope this has been useful for you. Also, hope you have a wonderful and safe weekend. Right? Don't let the news of new cases bother you. Right? I know we had one yesterday. Right? I mean that's more than the 0 that we've had for like the 20 days previous. Right? So on the island we've been doing really well, but you know it's unfortunate. It really is unfortunate. But we kind of need to keep up the distancing and to keep up the discipline, right? Even with so few cases coming in. Yes, it can be. I do think that we can start relaxing a bit, but we do still have to be vigilant. We do still have to be doing our part. I mean, look at what's happening in New Brunswick right now, right? They had no active cases for ages. They were doing way better than Newfoundland was doing for quite a while. But now there's this medical professional who came back from Quebec and apparently decided that they didn't need to self-isolate, that they didn't need to declare it for whatever reason. I guess they thought that it was just something that didn't apply to them. You know, it's easy for people to think that, I guess. It's oftentimes people think, hey, whatever. I'm not sick. I know I'm not sick. I don't need to self-isolate then, right? But turns out, hey, guess what? He was sick, right? And now this person could have spread it to up to like 150 other people. Could have been spread from this one person, a medical professional, someone who damn well should have known better, right? Um, who might now be the initial patient for a large cluster in New Brunswick. And as the next few days unfold, a few weeks unfold, we'll start seeing the full ramifications of that. So it does show that while we can maybe relax our restrictions a bit, just because there's no cases right now doesn't mean there can't be another calls cluster or a case like this guy in New Brunswick that end up with another big influx. Now, of course, if you're staying home and you're not going out of the province, most of the time, like the cases, they're going to have to come in from outside, right? Because we're down to what? We've got like 3 active cases now. The chance, that we know of anyway, but the chance for community transmission seems pretty low. But we still had to be vigilant. We still had to be doing our part and especially anyone going to and from provinces or countries or anything like that needs to realize that this whole, like, 14 days of self isolation when you come in is not. It's not just a recommendation. It's not like, oh well, if you feel sick, do it. But if not, like, who really gives a shit, you know? But even people that should well know better, right? Like medical professionals, apparently are not immune to this sort of pernicious notion that rules for thee and not for me kind of thing, right? Oh well, I'm not sick, so it doesn't really matter. I can do what I want. But those other people, they should isolate. All it takes is one. All it takes is one, and there's potential 150 new cases in your province that previously had zero, right? But anyway, I don't want to be here preaching to the choir about COVID-19 or anything. Just, it's an object lesson, I suppose, to glean some sort of positivity from what happened, or what's happening in New Brunswick, is that it's an example of what can happen when people let their guard down, when people think that the rules sort of can apply selectively. But anyway, thanks for being with me here for another week, and I hope that you know distance teaching has been useful and productive for you. If you got any questions at all, just you can even fire them off over the weekend. I won't look at them until Monday, but I'll get to them on the next stream. Thanks for being here. Thanks for watching. Stay safe, and I'll see you again Monday.